Okay, good morning, ladies and gentlemen, dear professor. My name is Mikołaj Lewandowski. I am a postdoc at the NanoBioMedical Centre of the Adam Mickiewicz University in Poznań. The NanoBioMedical Centre is located just next to the Faculty of Physics. So in the name of Professor Jurga, the director of the center, I would like to welcome you in our clean room facility. So clean room is a set of laboratories with ultra clean conditions for materials preparation. So actually at the moment you have a unique opportunity to see how the clean room looks inside, because the facility is not fully running yet. So the instruments are running, but in terms of the cleanliness of the rooms, it's not fully set. So today I would like to show you one of the techniques we have here, because in these laboratories we have a lot of techniques for materials preparation, like for solid materials deposition on surfaces or some objects with a precision of single atomic layers. And also for structurization, so we have some lithography here. So after depositing the layers, we can later structurize them, making some patterns, even at the nanoscale. So these clean room facilities are in general used also in industry, let's say in semiconductor industry, so for making like computer processors or things like that, where even a single particle of dirt can disturb the whole system. So coming to the instrument I would like to show you. So this is the atomic layer deposition apparatus. So in general it's like a stainless steel box where we have some vacuum. So we have vacuum pumps which just evacuate the whole space. So we have some even more idealized conditions for materials preparation. Then we have several chambers. So this is the load lock. So a place where we put our sample. So in general I can show you. So at the moment.
Yes, it's.
Continue, please.
Okay. So here we have a typical substrate for materials deposition. Like this is a silicon wafer, which I can put inside the chamber here. Then I can close the lid to the load lock. It is sealed with a Viton seal, and then we can evacuate it. So we have a vacuum inside. And later, our sample is transported to the second chamber, which is here. This is the reactor chamber, where the deposition process takes place. So what we can do with ALD is we can deposit single atomic layers of oxides or nitrates of many elements. And what is important here is that this deposition takes place from the gas phase. So we just expose our sample to a combination of gases which react on the surface, forming an atomic layer. And by repeating this process several times, we can just perform a growth of the layer, just layer by layer. So really with atomic precision. So underneath the reactor chamber, here are the so-called precursors, which are bottles with the gases we can use for the deposition process. So we have some precursors for metals. So for example, if we would like to make, let's say, hafnium oxide. So hafnium oxide is made from hafnium chloride and water. So the chemical reaction between these two components produces a layer of hafnium oxide on the surface. And right now, I will switch to presentation, which I have here. Okay, so this is the clean room team, I would say. So Dr. Mariusz Ancelewicz, who is the leader of clean room, then it's me and Dr. Błażej Szajbe, who helps us here. And on the images, in the top left corner, you can see this ALD reactor, and slightly lower, you see another instrument we have in the clean room, which is ultra high vacuum evaporator. But this is a completely different technique. It's not chemical vapor deposition. It's a physical vapor deposition. So you don't deposit materials from gas phase, but from solid phase. But this will be a topic of a different talk. So right now I will show you a movie on how the atomic layer deposition works. So I will just use the YouTube. Okay, so this will show how ultra-thin films of hafnium oxide can be formed by atomic layer deposition from the gas phase using hafnium chloride and water. So here you have the precursors, and here is the reactor chamber. It's very similar to ours. So you put some sample inside. For example, here they put fiber optic cable. They put it inside the reactor, close it, pump it to achieve a vacuum. And here they have the precursors which are needed for this. So first they expose the sample to a pulse of hafnium chloride gas, and you will see what happens on the surface of this material you want to cover. Yeah, so the hafnium chloride, the gas goes everywhere. It also goes inside the wire. And on the surface, you can see some very first reaction. So we have the hafnium chloride gas molecules attaching to the surface, also by chemical reaction. So what is important here is that this surface should be hydrated in order to form bonds with the molecules. So you see that the surface was saturated with a complete layer of hafnium chloride, and now a pulse of water comes, and the water reacts with this hafnium chloride, forming hafnium oxide. Yeah, so after this pulse, you can see that you have just a single atomic layer of hafnium oxide. And by repeating this process, yeah, again, hafnium chloride, water, you can grow just layer by layer ultra-thin films of hafnium oxide. And now you see, yeah, we are going again out of the fiber optic cable. So what is important for this technique is that the deposition is from the gas phase. So even if you have porous materials, like for example, we had a implant, yeah, like bone implant here, which some medicines gave us, and this implant had the structure of a foam, yeah, so it has a lot of pores, so it was a very porous structure. So we are able to cover this implant with a biocompatible layer everywhere, not only on the surface, on the very outer surface of this, but also inside the pores, yeah, so it's fully covered. Of course, this process is controlled by a computer, which is here. So you just write the recipes, which precursors should be used, how many cycles should be made, so how many atomic layers you want to produce. Of course, we have a lot of precursors here, not only for hafnium, we have for aluminum and titanium and other metals. We also, apart from water, we have also nitrogen, so we can form not only oxides, but also nitrates of these metals we have here. And you can make a layer which consists not only of let's say hafnium oxide, but you can make like multi-layers, like hafnium oxide, aluminum oxide, hafnium oxide, and so on. And so you can really design some atomic coverages. And I can show you one more slide I have here, which really shows the advantage of this technique. So this is just a second. Yeah, it's this one. So at the very top left corner, you see that there was a substrate which was structured. Yeah, so there were already some rows like nanowires, and the light covering you see here was made with atomic layer deposition. So you can really cover all the pores and holes in the sample with atomic. Atomically, with atomic layer of some material, like you see that the layer is very uniform and it goes everywhere. And let's say on the bottom right corner, you see another example. So you have some nanotubes. So these are zirconium oxide nanotubes, which you can also cover just with a single atomic layer. It doesn't matter that the nanotubes are randomly oriented and so on, because the gas will go everywhere. So that's it for this short presentation. If you have any questions, then please ask. I'm here to answer your questions, and you are also encouraged by Professor Stefan Jurga to visit our NanoBioMedical Center to see all the laboratories, so we can organize a guided tour for you. Thank you very much.
Thank you very much for excellent presentation. Now it's time for the question or comments. Yes, please.
So what kind of this?
First microphone.
Moment, just moment. Yes, you can ask.
What is on this side, which is look handle type, I think, a stick type.
Could you repeat this?
Handle type. Handle is attached with the machine, which is on this side. What is use of this handle?
On the left, on the side, all right.
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 On the front of the machine.
In front of the machine, what is
the equipment on the front of this machine? The computer with computer. Yes. What is this?
Yeah, this one.
Yes. This one.
Okay, so this is just a magnetic transporter, let's say. So we have a metal tube, which is non-magnetic, and a tube which is inside of this tube, which is magnetic. And here we have a magnet. So if we move the magnet, then the inner part also moves together. And using this, we can just transport our sample, which is lying on this rod, to the other chamber. So using this magnet, just by this motion.
And how many time required for this process?
How many time does the process take?
Yes.
It depends how many layers you want to deposit, because for a single atomic layer, these are just a few seconds. Yeah, you just hear the very short pulses of gases, like just click, click, and that's it. And you have a single atomic layer of material. But if you want to grow layers of, I would say, 50 nanometers thick or something like this, then you have to spend some 1-2 hours, something like this.
The gas HFCl, fume chloride, which is already present in this machine, or we externally enter?
Slower, please.
Okay.
Slower. Could you repeat?
The gas HFCl, which is already present in this machine, or we put externally?
Professor, could you repeat the question?
Please repeat your question, because
the gas
broadly.
The gas, yeah, I know that the gas.
Sorry, you could not get me, Bolo. Once again, I repeat my question. I have a question about HFCl gas, which is already present in this machine, or we put externally in this machine for a reaction.
This hafnium chloride, yeah? Yeah. Okay. So this precursor which you see here, yeah, we have let's say 4 spaces for different precursors, and so at the moment, as I said, we have here a precursor for hafnium, for titanium, for aluminum, and for I don't remember.
O3.
Yeah.
O3.
Okay. All 3.
And you can,
yes.
yeah, and you, yes, all of them are here, yeah. So you just, and they have numbers like A1, B1, C1, and so on, and you can choose which one do you want to use. And of course, you are free to change these precursors, yeah. They are relatively expensive because one bottle costs like 2,500 euro. But if you have a bottle with different precursor, then we can just disconnect, put this one in the cabinet, and install a new one. There is no problem. Yeah? So we are quite flexible with this.
Okay, our students have a background, biological background. So could you give any example to application your research in the practical? Okay.
In biology.
In biology, of course, yes. Yes.
Yeah.
Point of view crops.
Yeah, in biology, as I said, it can be used, for example, in let's say biomedicine for this implants to cover an implant with a material which has a very high let's say friction resistance, yeah, because this is important when you are putting some bone implants, yeah, to have friction resistance, to increase the hardness, to increase biocompatibility, things like this. And for real biological objects, it would be difficult because the samples we put here are evacuated to vacuum. So if we would put any organic material, then this would be a problem, yeah, because it would outgas a lot of water and so on. So this would be difficult. But so this what we use it right now is for some protective coatings, some functional coatings, and like biocompatible also. And for the biologic application, we have a lot of other instruments also, which you will see in the other seminars we will show.
Okay. In the future, I think another equipment with great pleasure we want to see, because our student, foreign student, wants to know how we use for the future, for the research, you know. So I think I asked and I talked with Professor Jurga on it, and I think next presentation we will play in this way. All right?
Okay.
Yeah? All right. Any more questions? Any comments, please? No? That's all? Yeah. Okay. So thank you very much for excellent presentation once more.
Thank you.
And we see next time, I think. Yes.
Okay. Thank you. Bye bye.
Bye bye. See you later.